Hey everyone, we're back at Hack.Summit. We've got an incredible speaker today with you. It's Chad Fowler. So Chad Fowler is the Chief Technology Officer of Six Wonderkinder, also known as Wunderlist. He's either authored or co-authored 8 books, including The Rails Recipes, which is a bestseller, The Passionate Programmer, also a bestseller, and also contributed to the 4-Hour Body. He is a creator and contributor to the International Ruby Conference and RailsConf, and he speaks fluent Hindi. He's educated an enormous number of developers, well-known blogger. Chad, so grateful to have you here today.
Well, thank you for having me. It's a really good thing that you're doing. It's kind of amazing. When you first started talking about it, I was not expecting it to be so massive, but I'm really pleased to see that it is, because it's all for a good cause.
I agree, yeah. I mean, it's just kind of a testament to kind of the giving nature of developers, that they want to come out here and support these nonprofits. And I've been blown away by the reception. We didn't expect it would be this big either. So it's very humbling to see the turnout. So for the audience, if you guys would like to ask questions to Chad, you can do that in the Q&A panel. The number one question, as voted by the audience, will receive 1 hour free mentoring from the participating speaker of your choice as part of Hack.Pledge, which is a movement we've launched this week for programmers to help each other become better programmers worldwide. It's a New Year's resolution to either give or receive 1 hour of mentoring. So you can either pledge to give an hour or receive an hour to help you in your time of need. And that's at hackpledge.org, and we'll talk about it a little bit later. But for now, I'd like to turn over to Chad. Chad, I'm just going to be here on mute, and my video is going to be off. If you need anything, I'll be here, okay?
Okay, thanks.
All right, take it away.
All right, so I am going to talk about an idea and a bunch of stuff around it that I've had for several years now that's been kind of driving the way I work in software. And I'm going to share my screen so you can see. So there we are. The idea is around building software that can be thrown away. So in, I guess, June of last year, I wrote a blog post called Immutable Infrastructure, Trash Your Servers and Burn Your Code, or something like that. And it was sort of the culmination of a bunch of things that I've been doing around trying to figure out how to write software that can survive for a long time. If you sort of survey the industry, we are pretty bad. We sort of suck as software developers. We don't do a good job of delivering projects. These are some sort of just dumbed down numbers from the Standish Chaos Report, which show software successes and failures over the years. And I think this is up through 2009, several years. And you can see the green bar at the bottom, that represents successful software projects delivered. And the red one is failed, and the stuff in the middle is challenged, and they define challenged as being substantially over time or over budget. So to me, that's also failure. So if you look at it as software developers, as an industry, we tend to fail to actually deliver software projects, sometimes at all, and most of the time on time or within the budget that we actually plan to deliver it. And then when we actually do deploy these things, we actually finish the software. On average, I would say, and it's literally just me saying from my own experience, that software ends up getting killed. So 5 years in, 6 years in, something like that, software projects end up being replaced. So if this is true, it means that the software we build is very lucky if it ever gets this bad word associated with it, legacy. So the software that we end up eking out into production and actually getting people to use over the years, it falls into this category of stuff that nobody wants to touch. That's a pretty sad state of affairs. You could barely, as an industry, deploy something successfully, and when you do, it's pretty much immediately hands off, something that people are grossed out by having to even think about touching. And there's a reason for that, though. The reason that legacy has become a bad word in our industry, as opposed to being a good word in almost every other field where you're leaving something for future generations, is that it's hard to maintain legacy code. It's hard to change the code. It's hard to even understand it. And so we end up with these huge, tightly coupled systems. So Even Rails is a fairly new thing on the scene. I mean, it's 10 years old now, but in software terms, that's still pretty new in the enterprise world. I've seen projects that just have huge layers of tightly coupled Ruby code, where you change one thing and you just have no idea what else in the system is going to hurt. And the sad thing about it is, this is the default setting. And by the default setting, I mean this is what we're going to do. If you get a team together and you're not really thinking, and you're just trying to build something, you tell the team to build something and deliver value, they're going to create this thing that is probably a huge tightly coupled system. That's the default thing that they're going to do, unless they're really being mindful and trying to do something different and trying to build something that can survive. So by default, we have trouble creating software at all, we have trouble launching things, and then we create these things that are really, really hard to change because of the way we architect the systems. And it's just human nature. You want things to be together, you start typing, you start building things up, and the time to start breaking stuff apart doesn't become clear until sometimes it's just too late. And then if you're working as a professional software developer, you hate the look of the screen. You run into these things where like you're doing the right thing, or you're trying to. You're doing test-driven development, or you're writing automated tests after the fact for your software. But the test suites themselves become a huge maintenance hassle. They take sometimes an hour to run, sometimes longer. But even minutes to run is painful when you're trying to get a fast feedback loop and be constantly moving your software forward. And not only that, the tests are really brittle. They break all the time. They break from time zone changes and external dependencies and who knows what. And you pretty much constantly get into these situations if you go from team to team, as I've done when I was doing consulting, where you have a test suite and the team just gets used to some portion of the tests failing, maybe at random, and that's just the way things are. So a test suite is sort of mostly green, that's okay. And it becomes stressful, and is, again, hard to work with. And because of all these things, your assurances are gone. So it's scary to change things. It's hard to test them. You're not 100% sure that your tests work. I mean, even if they all were green, you don't know that you've covered everything, because that's the nature of software development. And so you become afraid to deploy. And because you're afraid to deploy, you do it less often. And the less often you do it, the scarier it becomes, because the more change each deployment introduces, you know you're going to hurt yourself when you do it. Then finally, you get yourself, even if you're doing things sort of right, you get yourself in this mode where you're going to need to upgrade your technology. You know, what is the bleeding edge at the time you start a project? If you're successful and get it in production, will become leading edge and then stable and then eventually need to be replaced. You know, maybe to use the Ruby example again, maybe you're still using Ruby 1.9 and we're now into several cycles of Ruby 2. So it becomes very scary in these big monolithic tightly coupled systems where you're afraid to deploy and you don't change them very often to upgrade the technology. Even when you don't have to change any of the code, you just don't know what will happen. I've seen it in code bases where we were on Rails 2 at a company for years after that technology was obsolete, and we wouldn't even do point releases. We were backporting security patches because we were afraid to upgrade the core technology of Rails because we didn't know how it would affect this big, complicated system. So you get stuck in the old technology, and you have to keep reinventing technology that is now the status quo in your old tech stacks, which is a serious pain, and it burns developers out. It's no fun. It's not business value added. And then smart developers come along, and they see these monoliths, and they see this crazy mess, and they build abstractions, and they do it because they must. There's really not much of a choice. The code is complex, so they try to make it less complex by layering things in abstractions and separating code as much as they can. But what you end up with is like the design pattern soup type situation where you have so many abstractions it's hard to actually find the core logic of the system. And the sad thing is, in a lot of the things that we build, though the systems become complex, the core logic itself is actually very simple and shouldn't be obscured by all these crazy abstractions. But this is software systems, and we're a pretty new industry. Not all systems are like this. And several years ago, when I started exploring the idea that the term legacy in software shouldn't be negative necessarily, I looked around at different systems that don't have these same problems. You know, like if software dies after 5 years, what's something that's still useful after much longer than 5 years? An example might be cars. We're still driving around ancient cars, ancient by car standards anyway. Another example is bodies, such as the human body. I've probably taken care of my software systems over the years way better than I've taken care of my body. So it doesn't really make sense that I should still be here when my software systems have failed and died. But bodies and cars share some different characteristics, bodies and mechanical systems. And as I started digging deeper, an interesting concept came up from biology, which is the idea of homeostasis. And homeostasis describes an organism's ability basically to just self-regulate. So the body is filled with all these different competing functions that, if left unchecked, would take over the system and actually destroy the system, but then other functions, other organs, other cells control and counteract the negative things, and you end up with homeostatic balance, basically. So the brain controls the whole thing, the liver has one function, the kidney has another function that might be at odds in some cases with the liver, but the entire thing balances out. And when it doesn't balance itself out, it can lead to disease or death through something called a homeostatic imbalance. So this is how the system of a body, one way the system of a body can die. And oftentimes when people die of natural causes, generically, this is essentially what's happening. But the good news is we are all dying right now. Everyone's dying all the time. And this is that thing that you've heard since you were a kid, that you're not the same person you were when you were born because your cells are being constantly replaced. As an approximation, you have 50 trillion cells in your body, and 3 million die per second. We don't know exactly how many because it's not actually possible to measure them. But you are being pretty much constantly refreshed, kind of like a car too. The parts of the car might not be the same, but the car itself, the system, the car, still exists. So how could we make software that lives longer by mimicking the way these organisms work? What can we learn? So one piece that I would just plant in your head and move on is that small pieces are much easier to deal with and much more likely to live. An example of a small piece of a software system might be a cell, like if you try to use the biological metaphor. So the question you can ask yourself is, what is a cell? Because the cells are the things that are always getting replaced, right? What in software is a cell? And an obvious answer to that is just tiny components. Now, a component itself, it's a term that we use abstractly in software, but we all have our own definitions of it. When you stick the word tiny on the front, it means something a little more specific, which is just small pieces of granular functionality that, if we apply them to the biological metaphor, are like cells that can be replenished and replaced while the system lives on. So we have cells, and then we have systems. And the system in the biological metaphor is like your body. When I was preparing a talk on this idea of making legacy software a good thing, I asked my Twitter followers, what are the oldest surviving software systems that they regularly use? And I got a bunch of answers like these, a lot of them Unix related. No surprise, since that's also a very old suite of tools and operating systems. And what I saw when I looked at that list is that I saw either really well-defined systems, such as X windows. And when I say well-defined, I mean systems that are made of clearly documented interfaces of components. Or I saw really small things, like the grep command in Unix, or the od command. And Unix is famous for being a collection of tools that do one thing well and have very simple interfaces between them. And so, again, this sort of matched the idea of systems versus components being a way to build up things that can survive over time. You could replace the grep command, like with ACK, for example, and it doesn't change the fact that you're using Linux. Earlier in my career, I worked at a large company, and we had probably the oldest living software system that I have encountered, still to this date. It was a Honeywell Bull mainframe, actually a set of them, on top of which we had a custom RDBMS. We had built a TCP stack, since that didn't exist at the time that we put the thing into production, and a bunch of other custom software that was really kind of low level. It was just this Frankenstein of a system. But it had been living for, I believe at the time, 30 years. And it was a Honeywell Bull, as I said. There was a team called the Bull Exit team that was running a project called the Bull Exit project. And the Bull Exit team was actually older than any team I had ever been a part of either. And the goal of the Bull Exit team was to get off of the Honeywell Bull mainframe system because of the huge liability of having all this crazy stuff. The problem was, it wasn't that we were locked in somehow. It was actually that the Honeywell Bull system, the way it had been built, was done in such a way that its users would not tolerate a replacement with modern technology. So we tried and tried, and we could never come up with something fast enough or something that had the user interface they wanted. And on top of all that, the Bull was actually really easy to maintain. And looking back on it, the reason for that is the entire system was made up of tiny little subcomponents, some of which were even auto-generated by Ruby and Java code in later years. Tiny little subcomponents that could all be replaced. And we hadn't yet found a system in the more modern world that had those same characteristics that allowed us to evolve it over time without fully replacing it. So we were stuck with the Bull. So how do we build something like this that will last for 30 years or 35 years? I think the Bull actually made it 35 years before it was replaced. In recent years, I have turned to what is now a buzzword and was not when I first encountered it, but microservice architecture. And this is a picture of Fred George, who I think coined the term and did a wonderful presentation that is available online from the Barcelona Ruby conference a few years back. And the idea is just creating a system out of a collection of very, very small services that all have one small job. So nothing new, but somehow it's a new take on an old idea applied to modern web and service technology. So based on all of these ideas, I work at Wunderlist. We create Wunderlist. And when I took over as CTO a couple of years ago, I took all these ideas of legacy software as a good thing, and microservices, and the biology metaphor, and I put together some informal rules and ideas that we would follow for the creation of Wunderlist, which actually culminated in the release of Wunderlist 3 in July of this year. And the goals here were, I wanted to reduce coupling, I wanted to remove the fear of deployment. We needed to be able to deploy all the time. When I first got there, people were really afraid to deploy because they had had problems with scalability and system outages. Reduce the chance of cruft, and you can define that in almost any way you want, but one way would be code you don't know what it does or you don't even know if it's used. I wanted to make it trivial to change code. So you just change it, and then you feel free. You can just keep going, keep changing things. And when someone has an idea, they just do it and deploy it. And so here are some of the things that I communicated either formally or informally to the team. First one, maybe this is kind of common knowledge now. If you're reading along, if you can focus the slide well enough to see it, my brain, I don't know about yours, but my brain when I read code actually just filters the comments out. Like I don't even see them because it has been trained over the years that comments are worse than useless because they don't connect to the code. There's no way to validate them. And in general, they do more harm than good because they can be wrong. But so this is sort of common understanding. Not everyone believes this, but a lot of people believe this. I would say that tests are also a design smell, and this one is probably a little less popular of an idea. But if you find yourself spending more time in your tests trying to make them work, and I don't mean thinking about the design of the system, but just working on the tests, it probably indicates a bigger problem with your system. My goal now is to write code that is in a technology simple enough, small enough, and disposable enough to where tests might even be a waste of time. I once had a chance to pair with Kent Beck, who I think spoke yesterday in the Hack Summit, and we were talking about TDD, and I encountered something that I thought would be a weird thing to test, and he said, you should just test anything that could possibly break, which was, of course, intentionally subjective. My goal is to write code that can't possibly break wherever possible. And one way to do that is to write only tiny components. Now, on this slide I say code is this big in quotes, and usually what I'll do is hold up my hands with my fingers apart and say, if code is this big, you can do really anything you want. You can, if it's no bigger than this, you can write your services in the Idris language as long as it's not any bigger than that, because any of us on the team could come along and read that much code and understand what it's supposed to do, probably be able to spot bugs in it. Worst case, if we can't understand it, we would understand it well enough to be able to replace it. And it would be so little code we could throw it away quickly and replace it in a language that we knew. But I think this is a good general idea to have in mind when you're coding anyway, that each layer that you're at in an application, whether it be an entire service, which is what I'm describing here, or even just a method, just keep it so simple that there's no question about what it does. There would be no way to break it. For Wunderlist, we are heterogeneous by default. And I think there's one of the questions in the QA later would be about our tech stack. Here's a little preview. For Wunderlist 3, I don't remember how many languages we have in production, even for the back end. And that's not counting the fact that we have cross-platform clients, iOS, Windows, Android, et cetera, so we're already heterogeneous. But our service layer, we have at least Ruby, Scala, Clojure, Haskell, Node, Elixir, and so on and so on. This is for two reasons. One is because I actually want people, maybe even three. One is that I want people on the team to be able to enjoy themselves as technologists. And I've spent too many years in environments where people sit around at the coffee machine and daydream about how they could work somewhere else where they get to use some hip technology, but they're stuck in this terrible environment where they have to use Rails 2.3 and they're stuck, that sort of thing. So I just wanted to erase that. Like, that's a silly thing. That's a stupid thing to be sitting around complaining about for many reasons. So in our environment, you can try any language you want, and you can deploy it to production as long as it follows my rules. The other one, though, and the kind of more important one, is that when you are heterogeneous by default, and that's both from languages, runtimes, databases, whatever it is, then technology upgrade is just sort of part of your world all the time. And I mentioned technology upgrade being something that scared us in the past, but when you're heterogeneous by default, you're already in the process all the time of doing technology upgrade. That, you know, you're not stuck on one technology. You have a bunch of different components and different technologies, and it's much easier to change them, much easier to replace them. So even since the release of Wunderlist 3 in July, we have rewritten many of the underlying services in languages and runtimes that perform better just to optimize and save money, but none of our new users knew. So we've done pretty massive technology upgrades without anyone knowing and without there even being a big project to do it. Now, to make this really work, the nodes, the actual services, the servers themselves should be disposable. So I spent a lot of time as a system administrator earlier in my career, and I remember being proud of having systems that were up for over a year, not being rebooted. Now that idea terrifies me because I learned over time that the longer a system is up and the more access chances people have to go in and mess with it, the less you really know how to recreate it. So we measure our uptime on our systems, and we hope that it's low, like maybe in the hours, maybe in days. I would love it to be in the minutes. So the nodes, the systems that are running, in our case it's EC2 instances, they are sort of like cells in their own way. And replenishing them means there's not really a chance to build up cruft by lazy system administrators, and we're all lazy when it comes down to it, making changes that aren't repeatable. And therefore we don't even allow any changes to existing nodes. And when I say we don't allow it, I mean in spirit. So every once in a while it happens, we don't enforce it. But whenever it happens, we feel bad about it. We know that it's the wrong thing to do. So we deploy things, and the only way to upgrade software on an existing server is to throw away the server and replace it with a new one. And as I said, people get to pick their technology. Because it's sort of a problem with this approach, but also a benefit, is to make it work at all, everything has to be automated. And in our world, everything is automated. So all of our deployments are automated. We can even go so far as to deploy systems and then throw away the keys so no system administrator could even get into it. We haven't gone that far just because it's convenient to be able to get in and poke around sometimes, but that would be probably a next step where we do all the deployments, we throw things away, so there's literally no chance other than terminating the system to get rid of it and change it. Just terminate it and replace it. And then for any of the languages and technologies we use, provisioning new services needs to be trivial. And so we have created our own set of shell scripts. We used to be on Chef, and in this new world of immutable stuff, Chef and Puppet and those sorts of things don't really apply. They made things more complicated for us. So we replaced it with a very simple set of convention-based shell scripts. You have basically one command to deploy a new service. You have to fill out one file. That's it. It's very easy. And so anytime someone introduces a new technology stack into the mix, they need to make sure it fits into our automated deployment system so that anyone else can deploy it by clicking one button or typing one command. And then we always need to be changing things. So that's one of the biggest lessons I learned from extreme programming is when something is hard, like unit testing or code review or whatever, just do it all the time because you will find a way to make it okay. And deployment has been scary in the past. So we are just constantly replacing nodes. And we will probably move to a point in the future where we're replacing nodes automatically all the time. Hopefully, as I said, in less than an hour after they're born, because old nodes are scary nodes. Then in a system like this, where things are distributed, this is a picture of one of the creators of Erlang, Joe Armstrong. You need to assume that things are going to fail. And I think that the assumption that things can maybe not fail is what leads to a lot of the brittleness and the unnecessary layers of abstractions in existing systems. So rather than spend all of your time trying to make sure it doesn't fail and being afraid to deploy anything. Just monitor everything. And in fact, I would say you favor monitoring and measurement. Like that should be your religion instead of testing. I think TDD is a great way to do design, but it's not a great way to make sure you don't have bugs. And so favor measuring things live over testing them. And it really boils down to optimizing for mean time between failure versus mean time to resolution. If you spend all of your time working on increasing the time between failures in your system, then you're not going to be very good at resolving the problems when they happen. But my philosophy is instead focus all of your time on very, very quickly resolving any failure, since you know that failures are going to take place in a system. And you can monitor more than just your technical stuff. You can and should monitor your business metrics. So this is a tool we built at Living Social when I was there that helped us figure out when technical issues took place that were not measurable by normal monitoring systems. So for example, there was a JavaScript error on a web page that led to the login form not working properly. We could see that logins or new signups were dipping, which are business things that we cared about, even though there was no real error taking place, like no crash happening. And this is a very important thing to do. And then something I did when I got to Wunderlist is we were so afraid of deploying and so afraid of change that I just started forcing the worst thing to happen under controlled circumstances. So I would start removing servers from the cluster and get to the point where we were just very, very close to the metal, barely could survive, and get the team used to recovering from that. And we were able to do that in our case without actually crashing the system, but we were able to watch the graphs and see that the system was barely keeping up. And given the fact that we have this kill and replace system, it also allows us to very easily introduce new pieces of code or new operating system versions or whatever it is in small pieces. Monitoring everything, we can see the effect. And so we get this idea, this canary in a coal mine style thing where you put your code out and you see if it starts generating errors or it starts having an effect on the business metrics, and then you deploy in waves so that gradually over time your system is replaced with the new code, but all the while you've been able to monitor the effect of the new code without going fully over to it. So some things we haven't really gotten into yet, but are probably the next phase for us, this homeostasis thing. When you think of like the parts of a body in the way that that homeostatic balance would work and compare it to a system, this is just a diagram that I stole off the web somewhere of a generic web architecture. You could think of this as like organs in a body. And you could imagine, app servers doing something that create pressure on a database and start hurting it. You could put rules in that actually cause the systems to regulate themselves, and it could all be automated. And that's one of the next things that's on my list for us to do. Other companies are already doing a lot of this kind of stuff, like Netflix and Pinterest. Netflix is well known for their Chaos Monkey and their Chaos Star suite of tools that do all sorts of crazy things like destroy entire availability zones and data centers and make sure the system stays up. Pinterest has done something really clever where they use Amazon's spot instances, which is basically like an auction for server instances running. The fun thing about those spot instances is you would never think to use them for production for long-running systems, because when your bid of a price is no longer competitive, they will just automatically shut down your servers. And Pinterest actually runs production systems this way. So that means they have to really be ready for failure, which is pretty fascinating. So you do all these things, you can adjust to meet demand. I envision our system eventually being this sort of pulsating constellation that grows and shrinks to meet demand automatically. and to meet strange circumstances in the system. Now that we have this collection of tiny components, we need a maintainable, scalable way to refer to them. And so we started off with Zookeeper, and we're now doing a bunch of things with Console. And my hope is at some point that you can just ask for a service and not need to know beforehand where it exists or who processes it or how. But that's all handled by service resolution. Maybe something kind of like the way PubSub works, where you just push stuff into a queue. Although, for all the benefits of asynchronous code, it's also just a pain to work with. It's hard to figure out. It's hard to debug sometimes. I like to think of async as a fallback when I can, but I favor synchronous actions just for the simplicity of them where possible. Reginald Braithwaite at Nordic Ruby a couple of years ago said something really interesting about Ruby, which is that Ruby has beautiful but static coupling. And it wasn't really a complaint that much, but it was talking about this very idea of abstractions layered on top of each other and the ability to extend the language and open it up and do all these crazy things. He proposed that we have something like bind by contract. So this is one of his slides where you would be able to call a method on an object somewhere based on what it does. Not based on its name, not based on referring to the object directly. This is a really interesting idea for a language, but it's also an interesting idea for a distributed service system. So what if you had some sort of system-wide routes file that could read like a strongly typed functional pattern matching kind of language, like Erlang or something, where you could federate to heterogeneous services? And this is not something that exists anywhere, but I wrote some pseudocode where you could imagine, based on different data coming in, fanning out to different services to handle things based on what you need to have happen. Not the name of a service, but the behavior that you need a service to support. So just food for thought. Another issue is to make this sort of thing work, kind of like the Unix philosophy of systems staying or using simple and consistent input and output. You need to have well-documented interfaces. So there's this thing called schematron for XML. We're probably not going to use XML. We have started using JSON schema to document our JSON in and out of all of our APIs. In our system, it's REST APIs plus asynchronous messaging, mostly over Rabbit. And we use JSON for the communication there. So JSON schema is a nice, simple format for documenting your JSON documents. And then, of course, we're validating them, generating parsers, etc. And if you glance at it, you can kind of see you have the ability to define the properties of an object and all their types and reference other objects, etc. So it's pretty powerful. You even have regular expressions and a host of various implementations in pretty much any language you can think of. So what we started on, we actually built it, and it's not yet deployed for various reasons yet, but I'm excited about, is a global asynchronous validation middleware. So every message that flows in and out of the system is asynchronously validated and then pushed into our monitoring system. So that way we could see if a client deploys something that starts speaking strangely on the protocol and it's not exactly right, then you start getting alerts. Or if someone deploys a new service that starts returning a string instead of an int for a field, you'll see alerts. So there are lots of different ways to do these validations. There's also lots of ways to talk. As Grace Hopper said, the wonderful thing about standards is there's so many of them to choose from. So we won't get hung up on the actual implementation, but you need something like this, I think, for these systems to work well when you're dealing with big federated systems. I'm going to do a quick time check. Okay. So probably one of the most critical things we did that kind of felt dirty when we started, to tell you the truth, is that each of these little services that we built should own and encapsulate their own data. So we started with a monolithic database. It was a relational database, Postgres, with maybe foreign key constraints and joins and all that sort of stuff, and we threw all that stuff away. Instead, we divided the domain vertically, and each service that would be about a certain topic in the domain would have its own database. The beauty of this was, one, it was very easy for us to partition the data and make it more scalable. It also allows us to benefit from what I was talking about with technology upgrade on the database level. So we could switch a database from relational to DynamoDB or Riak or something, and no one would know except for the one service that talks to that database. So a pretty typical encapsulation kind of thing, but this has made a huge difference for us in our ability to go fast and be fearless. It does mean that we don't have foreign key constraints. I'm okay with that. The trade-off is worth it, and frankly, as I have traveled the world looking at software, most teams don't have foreign key constraints anyway, even when they have a single database, sad as it may be. The data itself, we try to keep as small as possible. Now that starts to be possible because the services own their data and they encapsulate it. I have a crazy idea. We're dealing with large amounts of data at Wunderlist because we have millions of users that are active and constantly putting things out in and taking things out. My crazy idea is that we will move from having any large databases to each user having his or her own SQLite database. That is maybe the ultimate, maybe insane version of this rule, but it's actually not too hard to do, turns out. So maybe in another talk in the future, I'll talk about how that succeeded or failed. Now, Fred George, in his microservice architecture talk, he has a colleague named Bayes, I think it's Jeff Bayes, who created these principles for deployment, which are really valuable, and it's all about versioning. Once you get a bunch of different services out in production, the next question is, how do I upgrade them and know that other services can work properly? So they said that it's okay to run more than one version of a service at a time. And as I said, for the canary in a coal mine style thing, you need to be able to do that anyway. You can only deploy one service at a time. And this led them to changing things in all the right orders and naming things in all the right ways so that it would be possible to evolve a system without any kind of downtime, or any planned downtime at least, and without an unmaintainable mess. You could also, or should also, read up on this idea of must ignore from XML land. Basically, it's a philosophy for versioning XML DTDs or schemas, where, kind of like the way browsers have worked in the past, that when new elements exist, old clients must ignore them. This is a big mistake that we made and others have made that I've seen, where you have very rigid requirements, and every consumer, whether it be a server or a client, is so rigid on the data that it will accept that you start introducing new things and the clients crash, and that's not okay. Probably John Postal said it the best. This is his law: be conservative in what you do, be liberal in what you accept from others. That is absolutely a good rule to live by when you're developing distributed systems for the internet. So, problems with this approach. Well, one is when you start breaking everything up into microservices or into independent pieces, small components, however they are deployed, they have to talk to each other through potentially less optimal paths. So, for example, our systems still talk to each other through HTTP, mostly. This could be really slow. In practice, for us, it has not been, because in our REST APIs anyway, something that came along for the ride with this this desire to create tiny systems is we also created tiny requests. And we decided to favor breaking up requests and not trying to batch them together, so systems could make many small requests to each other that would be very, very fast. And this has actually made our new system much faster than our old monolithic system. The other counter to this is when you have a highly segregated system and heterogeneous one like we do. Since they're so decoupled, it becomes much, much easier than in a monolith to figure out where the performance bottlenecks are. So it's very rare in this new system of ours for 1.3 that we ever have a question when there's a performance problem. We know exactly where it is. We usually know exactly what change caused it. Whereas in the old monolith days, it's so hard with all the possible interactions of code. It's so hard to determine where performance bottlenecks are without ripping things apart. So I think in theory, these systems are slower than they have to be, but in practice, they're faster than the alternatives. I think there probably is a case to be made to start moving from microservice architectures to, again, monoliths that bring with them a lot of the ideas that people like us are learning, or the lessons we're learning in microservice architectures, to see if we can have the best of both worlds. It is a little hard to set up development, and when I say a little hard, I mean almost impossible. Like even just to come work with us right now, if you wanted to get every single service running on your computer so you could develop independently, it would probably take you a couple months, and it wouldn't be worth it. So the good news is we don't really need to do this because we can test each service independently. And although I was saying tests are a design smell, it doesn't mean that we don't do TDD and benefit from it. We can TDD these services. The interfaces are so simple and the code is so simple that it's pretty easy to change them and then gradually deploy them so that you can feel confident about the changes as you're making them. I mentioned no referential integrity. Yep, you just have to deal with that. Maybe there's no unified view of what the system is. That's something that we have to compensate for. Now, I would argue that there isn't really such a unified view in most big monolithic systems either, but it does get more complicated when things are spread across a heterogeneous fleet of services. The main counter that we have for this is that we have developed consistent conventions for how the systems will talk to each other, how they'll be structured, what their namespaces look like. So although it may not be clear where the code is for a certain part of the system until you really know your way around, at least you know how the components talk to each other. And that is the end of my canned piece of the presentation. So am I still here, Ed?
Yeah, and it was all great. The audience was enthralled by it. The comments have been pouring in. Lots of interesting conversations have been spawned from all this chat. That was an incredible presentation. Lots of great stuff in there. And as you've been speaking, we've done some polls of the audience. And if you just switch over to the polls tab, Chad, I don't know if you can see it. You'll see what the audience is saying here. Mm-hmm. So we tried to ask some questions that were relevant to what you were speaking about today.
Interesting.
So yeah, you can feel free to browse this. I'll kind of go over it real quick. So how much time do you spend per week maintaining, extending legacy systems? The most popular vote was more than 10 hours per week. So that is, people are spending a significant amount of time maintaining legacy systems and extending them. So it's definitely eating into people's time here. How often do you release updates to your application or service or technology? Typically, it's monthly. So not a huge amount of continuous deployment, continuous integration happening here.
That's terrifying.
Yeah. But I assume that many folks are kind of moving in that direction over time.
I hope so. That just sounds like a sad way to live.
We can actually ask that poll too. We'll just ask that poll. So anyone on the Hack Summit team that can hear me, why don't you go ahead and just add another poll here for the audience moving towards continuous deployment? Are they doing that? Do they have plans to do that or not? let's keep going here. What are the oldest surviving software systems you regularly use? Most popular answer is a Unix-based system, but a variety of different answers in there. And then I put in this poll myself. What's your coding style? Be honest. This is after you put your slide there about code comments being something that you have to maintain over time and actually adding kind of cruft. Most people are commenting lightly, not heavily, and a fair amount of people are doing self-understanding code without comments at all.
Or so they say.
Or so they say. Well, I asked them to be honest, so it's an anonymous poll. No incentive to lie here. So I hope it's accurate data. And then I asked, is your company's architecture based on loosely coupled standalone nodes? Most people shockingly say no, and they have no plans to move to a loosely coupled standalone node architecture. The second most popular answer is that they are moving there over time, even though they're not doing that today. And then the last poll I put in there, what do you think of Chad's vision of calling services not based on their names, but based on their functional behavior to fulfill a requirement? I thought that was a really, really interesting idea, Chad. And the audience agreed with that. Overwhelming majority agrees that it's a really interesting idea that has potential. I would love to see that actually happen. Do you have any ideas for the implementation for that? Like, would there be a central directory that would map names to functional services? What's your vision there?
I don't know. I mean, it really is Reginald Braithwaite's idea more than mine. I just extrapolated it to be about services instead of OO. But I don't know. I honestly just don't know. I've played around a little bit in Erlang with some ideas, but it's not been. It's more of a science project idea, and I haven't had time for it. I have to learn German first.
And then the last poll that we entered in there, by over a 12-to-1 ratio here, most people are planning to move towards continuous deployment.
That's good.
So that's good to hear. So we only have time for a few questions here. I guess one just this kind of thing I'm curious about. So you mentioned the whole idea of heterogeneous languages as something that you guys have embraced. Does that make it hard for maintenance in that programmers have to learn different languages to even get competent at helping out with someone else's system?
Yeah, well, there's definitely a barrier the first time you hit a language you've never touched, and I think the bigger barrier than the language is usually just getting the project set up and running. So you have to have a stack for Haskell and Scala and Clojure and Ruby and all these things running. So it means that we have to document everything pretty well in the READMEs for every repository. When it comes to actually switching gears, I can only speak for the team members that I've talked to about this in person. I think that we're all surprised at how easy that is. That like, I don't know Clojure very well, but I've been pretty productive in it. And the more I keep switching every day between many languages, the more likely I am to guess what a language probably provides. So it's sort of like the pragmatic programmer says, learn a new language every year so that you can become, you can change the way you think. We're doing this rapidly in real time all day, every day. And I think it's actually making us all smarter as a result. So it's kind of hard, but it's not that hard, and it really is. It's fun, and it feels worth it to me.
And for developers that are working in environments where maybe not everyone is kind of one of those 10x or 100x productivity developers, like a typical kind of IT shop, would you still recommend the kind of heterogeneous environment?
I don't know. I mean, what you're really saying is, if you were working with a bunch of average people, would you still want to do this?
Yeah, it's a nicer way of so yeah.
I think I would like to not work with a bunch of average people. And if I were asking myself the question about doing heterogeneous environments, and then I had to say, well, will this work in my environment because maybe the people aren't smart enough, then I would probably go find another job where everyone's smarter than me.
Makes sense. Okay, great. Let's go ahead to the audience questions. The number one question by far, with 341 votes, asked by Alex. Alex, you'll be winning a 1-hour session with a participating speaker of your choice as part of Hack Pledge. So he asked kind of a funny question here. What is it like having a world-class golfer as a brother? Do you ever golf with Ricky?
If I knew something about golf, I would probably think this was a funny joke, but no. I'm also Martin Fowler is not my brother. Uh, but no, I don't even know who Ricky is.
Huh. Okay.
You?
Uh, Actually, I don't. I'm not sure where that question came from. All right, next question by Danajar Hafner. What was the biggest decision in terms of technology you faced in Wonderlust? This is probably the last question we'll have time for today.
It was, well, it's hard to say, but it was how we were going to do real-time synchronization. So in Wonderlist 3, the way it all works is it's a cross-platform application. It's doing real-time synchronization of structured data that has to work across multiple people and multiple clients. So to be able to get this right so that we could literally, if you check off a task in a list and someone in another continent is looking at it, they will immediately, within a second or less usually, see the task get checked off. That was a big challenge. And it wasn't just a technology choice, it was a whole bunch of technology choices and the scariest decision we had to make.
Great. All right, maybe since that was a fast answer, we'll go to one more question here. Just kind of scrolling down the list to see something that seems pretty interesting here. Okay, here's the question. Do you think cloud infrastructure and computing can fully solve the immutable infrastructure and disposable components problem? If not, what's missing?
Yeah, I think they can.
Sorry,
Because
Chad, your audio cut out there.
am I still here?
Yeah, you're good. Keep going.
Okay. I think they can solve the problem. I think what's missing is that this has not been something that has been in the public perception for very long. And so there are now more and more companies trying to build things that automate this, but it's really just all about automation and monitoring, starting with the understanding that it's a good idea. I am advising a company called Luminal out of DC who is building what is almost exactly what I have described in the stuff that I've written by chance. We didn't know each other before that, but we connected because of their product and conference talks. And that's a really promising indication of what might be to come.
Okay, great. Well, Chad, I want to thank you so much for being here. It was very educational and informative, and I'm very grateful for your participation. The nonprofits are as well. If you liked what Chad had to say today, if you learned something, please go consider contributing to one of the 16 nonprofits in the coding space that's on the Get Involved tab that you currently have highlighted right now. Chad, any final words of wisdom before we depart today?
I have no words of wisdom, no, other than thank you.
Thank you too, Chad. Guys, we'll be back in just a few minutes with our next speaker. Chad, thanks again.
Bye.